Yeah. So are there any questions about last time? Like we finished the polynomial equidistribution. So which was that if a polynomial has leading coefficient irrational, then it is P of n for integer n, that sequence is equidistributed. And the key point was this van der Kolk inequality, which van der Kolk lemma, which goes from differences of a sequence to the equidistribution of all differences. So where is that? Yeah, if you have a sequence and all differences xh are equidistributed, then the original sequence is equidistributed. And the key thing here was this van der Kolk inequality, which I cannot explain too well. So that was the point. We did the proof. Are there any questions about that? Okay. If not, then let me move on. So I decided that I will not go into this.
Can I have a question? So, I just last week, last lecture, I have a question from the previous class. So, at the end, you were mentioning that this equidistribution thing that only tells you that for intervals or some simple sets you have that convergence, right? But that's a weak convergence result. So you have that for all sets whose Lebesgue boundary is 0, isn't it? That fourth thing that you highlighted.
Right. Okay. What did I say? Yeah, no, you're right. Right. Sorry. Yeah, that is true. Yeah, it is true for Lebesgue sets whose boundary has 0 Lebesgue measure. So the question is, so there was in the end this question whether this kind of convergence in equidistribution, whether we can say that for any set A, the indicator A of xk average converges to Lebesgue measure of A. That is not true for all A. As I said, A is, if you take A to be this countable set itself, then we have problems. So what Shaumendu is saying is, we also said that this is same as weak convergence of these measures called empirical measures. But that would mean that for any set of, so what does mu n converging to mu in weak convergence mean? Convergence in distribution means mu n of A converges to mu of A for all A for which the boundary of A has 0 measure under the limit measure. In this case, Lebesgue. So there is no contradiction because the set is dense, A is dense. Therefore, in such sets will be problematic. The boundary of A is everything. So that's what I meant.
Yeah. Yes.
Yeah. So, but you're right that it is true for all sets A, which for which the boundary of A has 0 Lebesgue measure, but that's usually never things like all Borel sets or something like that. Yes. Right. Yeah, whereas what happens is, so that so if you want to have convergence for more sets, for example, when some densities converge to another density, probability densities converge to another probability density, then you have a more stronger convergence over all Borel sets, in fact. So mu n, if mu n and mu both have density and the density of mu n converges to density of mu pointwise, then we can have even stronger statements like mu n of A converges to mu of A for all Borel sets A. But that is not going to happen if these are discrete measures like this. Right. Okay. So any other questions about anything so far? So next, I will go to this question. So the other day, Shaumendu had asked the question about something quantitative. Okay, the question may have been slightly different, but at that time, I completely forgot that I was planning to do one quantitative theorem. So this is a very interesting theorem, which will make the Weil criterion much more quantitative. Okay, so this is a quantitative version. Of equidistribution. Which is anyway equivalent to the Weil criterion. So it will be we will be quantifying the Weil criterion. So the question is like this. Suppose mu is a measure on the unit circle, okay? And so now I will actually move back to 0 to pi because I'm going to use Fourier analysis, and I don't want to get stuck in this situation where the formulas I forget. So, but of course you can transform from 0, 1 to 0 to pi, okay? So we can, equidistribution on 0 to pi is also clear, okay? And suppose mu hat of n is 0 for all n less than equal to 10 to the 5. So can we say how close is mu to m? By m, I mean dx over 2 pi, normalized Lebesgue measure. See, what we know is of all the Fourier, I mean, of course, for all n not equal to 0, so mu is a probability measure. So mu hat of 0 is 1, but suppose if all other Fourier coefficients are 0, then mu has to be equal to this one. But suppose what we know is that the first so many Fourier coefficients are 0 or small, maybe even more generally, maybe we only know they are small. Can we say that mu is close to the Lebesgue measure or not? And what is the sense of closeness? In what sense? I mean, so we take some natural sense of closeness on measures and say that, can we say that mu of, for example, mu of an arc, is it close to the Lebesgue measure of the arc, normalized? So that is what is being done here. So this is the Erdos Turan lemma. The answer is yes in the following sense. I think in Turan also there is an accent somewhere. Erdos Turan lemma says this. So mu a probability measure on the T, and m is uniform probability measure on T, then for any arc I. So arc is clear. Arc means anything like this. Okay. So for any arc I in the unit circle, if you write it as 0 to pi, it could be some a to b, or it could be something that comes around 2 pi. Okay, that is clear. But for any arc, so it's not for any set. For any arc, we have mu of I minus m of I. The difference is bounded like this. There is some constant c, maybe it is 100 or something like that. K equals 1 up to n, mu hat of k over k, with an absolute value here, plus 1 over n. Okay, so for any n, what is this saying? For example, look at the blue situation which I have written here. Suppose Fourier coefficients vanish up to order 10 to the 5. Okay, so mu hat, by the way, mu are real measures. So mu hat of minus n is going to be mu hat of n conjugate. So they have the same absolute value. They are 0. So what is this saying? Then we can apply this with n equals 10 to the 5. See, the first 10 to the 5. So here maybe I write 1 by n. It doesn't matter actually whether you write, because that's the same. But so the first 10 to the 5 Fourier coefficients are 0. So if I choose n to be 10 to the 5, what I get is the mu of I minus m of I is at most 1 by 10 to the 5 for all arcs. That's what this is telling us. Okay, so that is a way in which you get the closeness. More generally, you may not have exact 0, but if you know it is sufficiently small, then you get some quantitative. You have to choose n appropriately. If you make n very large, you don't have control on the higher Fourier coefficients. Maybe you have Fourier coefficient control up to a point. So if you can't make n too large. But then if n is not large enough, then this term is big. So you would like to choose an optimal n for which you will get something like this if you want to show closeness. By the way, this one, if you like, this is actually, what is this? This thing is actually So if you like, so we can define d of mu nu as the supremum over all arcs of mu of I minus nu of I. It is up to constant same as. So this is okay. Let me just say is a distance on probability measures on the circle. It's called the Kolmogorov-Smirnov distance. If you have seen Kolmogorov-Smirnov, you may see it slightly differently, but it's essentially the same. Okay, so it's a distance between probability measures. It's a bit stronger than weak convergence. Convergence in this metric is stronger than convergence in the weak sense. That is, mu n's converging to mu in distribution does not imply d of mu and mu goes to 0. Whereas the converse is true. If d of mu and mu goes to 0, then mu n converges to mu in distribution. So this is a stronger metric. So it's a better bound actually. It's a good bound. Okay. So this is what we want to prove, and we will get something amazing later as a consequence. Something about polynomials. Okay. So but I don't want to start stating what that thing about polynomials is. It will waste time. Whereas I can try to complete the proof of this. But maybe I give you a motivation in terms of if someone has seen in probability. So in probability theory, there is something, an advanced form of central limit theorem. Okay, so let me explain that. So you may have seen central limit theorem if x1, x2. The basic central limit theorem says, CLT says that if I take x1, x2 IID, expectation xi is 0, expectation xi square is 1, then if you look at Sn by root n, that converges to normal 0, 1, or just writing where Sn is x1 plus up to xn. So this one, to write out what that means, since normal distribution has, so this just means that probability this Sn by root n belongs to an interval AB minus the corresponding thing. Normal random variable belongs to AB. Okay, where Z is a normal 0, 1 random variable. This goes to 0 as n goes to infinity for all AB. Okay, so this is what central limit theorem says. So a quantitative version would be how close is this? How close is this in terms of n? This is going to 0 as n goes to infinity. Can we get a bound? You cannot. If you stick to these assumptions, you cannot get anything better than that. But it is of great practical importance. See, this is a theoretically important thing to do the theorem under minimal conditions. But for practical things, you want a stronger, you may have much stronger things here, more than this. But what you would like is to also strengthen the conclusion. So that thing is called the Bayesian theorem. It says the same as above. Let's take x1, x2, IID. Expectation xi is 0. Actually, IID is also not needed. I'm just saying in a simple way. Expectation, let's say mod xi cube is some gamma. Okay, actually, you don't need identical. If you have independent random variables, I think even if with independent, it's enough, independent. So you don't need identical distribution, but don't worry about that. Mean is 0, variance 1 as before, but the third moments are uniformly bounded by some number for all I. Okay, so the same gamma works for all I. If they are identically distributed, these are all the same. But otherwise, we want a uniform bound for the absolute third moment. Then what we can say is that probability Sn by U10 belongs to AB minus probability Z belongs to AB is bounded by, there is some constant over square root 10. So this constant may depend on gamma. It only depends on gamma, C gamma over square root 10. So you get a rate of conversion. This is true for all AB. So simultaneously. Okay, so it's a very strong bound. This bound, this is exactly like here. Here we are taking arcs. Here we are taking intervals, which is arcs in the real line. Okay. So you get a bound like this. So what the purpose of this is also similar. I mean, so the key step. So why I'm mentioning is this is an important, interesting theorem. We usually don't cover it in basic course because, of course, there are so many things one could cover. It's not possible. But it's a very important theorem. And the key element of the proof is very similar. What is the point? See, if you have seen central limit theorem, you know that is done via characteristic functions. You show that the characteristic functions of Sn by U10 converge to the characteristic function of normal 0, 1. Now you want to get this, you want you want to do that quantitatively in some way. But not only that, you have to have a way of quantifying this in terms of the closeness of characteristic functions. Characteristic functions means Fourier transform. So what you need is a lemma like this. Okay, so this is the lemma. So the key point of the proof is a lemma like this, that for any, if mu is any probability measure on real line, and let's give a name for Gaussian distribution. So let's call it M is normal 0, 1 probability measure. Then mu of AB minus M of AB. You can take sup over A less than B. Over all intervals, you can bound. How do you bound? And a very analogous theorem to this. You have to bound it in terms of the closeness of the Fourier transforms. Now, Fourier transform is not a sequence, but a function. So instead of a sum, you will have an integral. So you get a bound like this. C times integral minus t to t, let's say minus, let me call it minus L to L, mu hat of t minus m hat of t divided by t absolute t dt plus 1 over L. Okay, so you see the similarity between these two. This is okay. I have written 1 to n minus 1. It's the same if you write minus n plus 1 to n minus 1. That's the same thing. But you have basically mu hat of t minus m hat of t. You also let me make it 0 to L. Okay, no big deal. Because the other side is the conjugate. It will only give a factor of 2, which can be absorbed into this constant. Plus a 1 by L. If you can show Fourier transforms are close up to L, then the error 1 by L will show up. If they are equal up to L, then the error is only 1 by L. So this is the key element of the proof of this Bayesian theorem. We will not do the Bayesian theorem. Instead, we will do this. But pretty much once I do this, you will be able to prove this lemma yourself. And you can even then try to, if you want, look into the proof of this. So this I'm just mentioning for interest. The same ideas keep repeating. So what you need to know when learning analysis, so the thing is, things are not exactly the same, but they are roughly the same. So that's why some people tell that when learning analysis, especially, I don't know about other subjects, but in analysis, I mean, there are lots of theorems. Okay, there are much fewer proofs, and there are even fewer proof techniques. So you are best off if you learn the basic techniques. Okay, you cannot remember all the theorems. You will not learn all the proofs. Proofs are putting together proof techniques in multiple ways. So the number of different techniques is way smaller than, I mean, it's a large thing. That is what a good mathematician knows. But someone like Tao knows so many techniques. But that's still smaller than the number of theorems and so on. So if you just see it as theorems, this theorem has nothing to do with Bayesian and so on. But you have to understand the underlying technique is the same. Once you get that, then you see much more. I mean, then you can see analysis from a more global viewpoint and understand the connections. Anyway, so I'll just come back to this one, for which we'll find a fantastic application later. Okay, so that will be next lecture. But now let's try to prove this Erdos Turan lemma. How do we prove something like this? Any questions, comments so far? So you also see that this is, by the way, you also see that this is a quantification of Weil criterion, right? I mean, in the sense that if you have a sequence of measures mu k, such that the mu k hat of n is going to 0 for all n, then you can show from here that mu k converges to m, because these things are going to 0. So you will see that for large enough k, mu k is to m, the distance is at most 1 by n for any n. So that is how you get. It's a quantification of the Weil criterion. Okay, so how do we prove Erdos Turan? So basically the distance. So for those of you who have seen the Kolmogorov-Smirnov distance, you probably know it more like the difference between the sup norm between the cumulative distribution functions. It's usually done in the real line. So the Kolmogorov distance between mu and nu in the real line is usually defined as the CDF sup norm. But that and the sup norm over intervals are pretty much the same, up to a factor of 2, because this is just, well, okay, if I were to make it left closed, right open, left open, right closed, that would be f mu of b minus f mu of a. Then this would be fm of b minus fm of a. So that difference is f mu of a minus fm of a and f mu of b minus fm of b. So it's actually this and this are up to a factor of 2, the same thing. So what we will do now is introduce the distribution function. So that's what I mean. So that's what we do. So let's define it as mu of 0 to t for 0 less than equal to t less than 2 pi. So fm of t is going to be what? Fm of t is going to be t over 2 pi. Because that is the uniform distribution on 0 to 2 pi, right? So this is what we have. So we want to show the closeness of f mu and fm. That's same as closeness of measures of arcs, because this is pretty much up to a factor of 2, the same thing. So for that reason, let's define the difference in the distribution functions. And then, but I will subtract a constant a. So I can always subtract a constant so that the integral is 0. Okay, that is well, why we do that? Okay, so you'll see. Okay, so v of t is just basic. It's essentially the difference in the distribution functions, but in some way this a is like, here you started at 0. I mean, on the circle there is no starting point. In the real line we take from minus infinity to t. On the circle there is no way to. It's an arbitrary starting point we chose. The subtracting of a is somehow getting rid of that arbitrariness, but don't worry about it. It doesn't make any difference, because if I want mu of, if I is an arc, which let me make it left open, right close for simplicity, then mu of AB minus mu of AB is same as f mu of B minus f mu of A. Okay, so here this constant, maybe I give it some other symbol which I will never use. What symbol will I never use? Okay, let's make it capital A. Okay, f mu of b minus, so this will be f mu of open A close B, mu of open A close B is f mu of b minus f mu of A minus f nu of b minus f nu of A. Right? Actually, I want here not nu but m, right? So I just want m here. So if I want to consider a mu of AB minus the m of AB, m is always the Lebesgue measure. It is this, which is, you can write it as f mu b minus fmb minus of f mu, but this is same as v of b minus v of a, right? Because the difference cancels the a. Therefore, supremum over arcs mu of I minus m of I is bounded by 2 times the subnorm of V. Okay, because any such difference is bounded by VB minus VA. We can take both positive and negative values. Now we have subtracted A, and this is a difference of two distribution functions. It takes both positive and negative values. So I don't hope to get anything by cancellation here. So I just bound it by 2 times the subnorm of V. This is okay, right? So what we need is to bound the subnorm of V. That is the key point in the proof. But before that, I don't know if I'm going fast. I mean, is it clear, or should I explain something? Is it being clear? Okay, so how do we bound the subnorm of V? That is the question. Okay, we want to bound. So the bound we will do. So the claim is the claim. So let's break it into a claim so that we know what we are after. So we want to prove that subnorm of V is bounded by a constant times V hat of k. Actually, I chose the first one to be 0, but anyway, so V hat of k plus 1 over plus, I will write what it is. Okay, I'll write what it is. Omega V of 10 by n. Okay, what is this omega V? It is a modulus of continuity, but it's something subtly different. Okay, so you have to pay attention. Omega V of delta here, omega V of delta is the supremum of V of t minus V of s over s less than equal to t less than equal to s plus delta. Okay, of course, this is going around the circle, by the way. This addition is around the circle. So if s plus delta exceeds, you will go the other way. That's okay. That's not the problem. So that is always the case when I write. Sometimes it's convenient to write an interval, but you have to remember it is so modulo 2 pi. So that's there. But one thing you notice is that I didn't say that it is not mod V of t minus mod V of s sup over that over mod s minus t less than. That is the usual definition of modulus of continuity, but this is not like that. I have not put an absolute value here, and there is a ordering s less than equal to t less than equal to s plus delta. So it's a kind of one-sided modulus of continuity, which will be helpful for us. Okay, it's a one-sided modulus of continuity. Now, this is what we are going to prove. So this is, so from here, so how do we get the theorem from this? Okay, so proof of the complete, let's complete the proof assuming the claim. See, in some sense, what is mu minus m? Mu minus m, if we differentiate V, okay, you get f mu dash minus fm dash, right? But in some sense, the derivative of the CDF is the measure, right? So let me just write this. V dash is mu minus m. Okay, the derivative. So the derivative of V is like mu minus m. Hence, but this is not meaningful, maybe, but what I'm writing, this is just to motivate to connect with things we have seen. So what would be the Fourier coefficients of V and Fourier coefficients of mu? So if you look at what are the Fourier coefficients of mu? Mu hat of k is same as mu minus m hat of k if k is not 0, because m hat of k is 0 for all k not 0, right? So mu hat of k is that. But this is the derivative Fourier coefficient at k. But what is the derivative Fourier coefficient? You know that, right? It is so v hat of k is e to the minus I k x d v of x dx. Sorry, yeah. So v dash hat of k is either I think it is ik or minus ik. I forget which. V hat of k. Okay, so this we have seen. When you take derivative, the Fourier coefficient gets multiplied by I times k or minus I times k. It won't matter, so I won't bother to figure out. So even if everything I have written here is meaningless, that part is true. So I will leave that as check. That mu hat of k is ik v hat of k. Okay, plus minus. For all k not equal to 0. K equal to 0 is k equal to 0, it won't satisfy. V hat of 0 is 0. This side is 0, but mu hat of 0 is 1. So it's not 2. But there you have to take mu minus m hat of 0. That will be okay. Right? Okay. So this I will leave to check. It's very similar to what we have done before. Okay. So the motivation is here. So assuming that, what do we get? Hence, mu of I minus m of I, the sup over all arcs, we have already seen that is bounded by 2 times the sup norm of V. Which is bounded by, okay, 2c times sum over k equals 1 up to n minus 1, because V hat of 0 is 0. So I get mu hat of k divided by k plus what is omega V of 10 by n? Okay, what is omega V of 10 by n? Let's worry about that also. What is omega V of delta? When V is this. Okay, so when V is like this, when F is omega V of delta is sup of so V of t minus V of s, where s minus s less than equal to t less than equal to s plus delta, right? But what is that? V of t is actually f mu of t minus fm of t. So you get, when you take the difference, we have seen V of t minus V of b minus V of a is same as mu of the is same as mu of st minus okay, m of st. Okay, how do I upper bound this? I made a mistake actually. So this is the one-sidedness makes it very important to do it the right way. So let me just go back and slightly change things. Okay, sorry about this. But well, what shall I do? Otherwise, I will have to do V of s minus V of t maybe. Yeah, shall I do that? It's probably okay, but I will just confuse myself later. So okay, I will just sorry, but I will change everything. I'll change the sign of everything here from here onwards. Instead of f mu minus fm, I will make it minus f mu plus fm. Okay. So this is minus here and a plus here, and everything is a minus and a plus, and this becomes V of b minus V of a. So this part is again exactly the same. Now v dash is not mu minus m, it is minus mu plus m, I think. So, but everything is still the same. So what we get here is that instead of, but coming back to this omega v of delta, we get sup of vt minus vs over this. But that is mu. Now this is a negative and that is a positive. Okay. Now we know a bound, right? This is less than equal to delta. Because this is negative, so I can bound it by 0. This is delta by 2 pi if you, it is delta by 2 pi. Is that okay? I need to do it this way. Otherwise, okay, if I had set it the other way, I would have to define the modulus of continuity with Vs minus Vt. But okay. But anyway, for me, it's better to do it this way. Is this okay? So we get this. Because of that, here what we get is omega v. So omega v of delta here 10 by n, right? So we get 10 by n. So which is I can write it as 1 by n. Omega v of delta is delta basically. So whatever constants we don't care. So it is some other constant times. Because I have some more constants, I don't care, but you get this. The k equal to 0 vanishes because v hat of 0 is 0. That term is not there. So this is how you get, which is the final conclusion. This is what I wanted, right? That mu hat of k over k plus 1 over n. This is what I want. So assuming the lemma, assuming the claim, we have everything. So it's only I need to prove the claim. It's okay. This one-sided modulus of continuity, it's a trick. I mean, it is not, it is subtle point actually. Without that, I mean, you get into slight troubles. The problem is if you put the absolute value here, what happens is we have no continuity properties of mu. Mu is possibly even an atomic measure. We don't know how big mass it gives in a short interval, right? We don't have that. That is why the one-sided thing helps. I ignored this, but mu could give us, I mean, if it's atomic measure, it could give a large mass even on a very short interval. It need not be proportional to delta. If you have an atom inside, it's not even, it doesn't go to 0 as the interval size goes to 0. So that is going to create a problem, but we need only one-sided thing. So that is why this works.
Manju, what was that v dash mu minus m thingy? Maybe I'm missing. What is that?
Oh, which one? No, that was just to motivation to say that why mu hat of k is ik v hat of k. This is reminiscent of the derivative formula. When you take derivative and Fourier transform, you get ik times the original.
Okay.
So I was saying that you can, if you formally v dash looks like the difference of the derivative of the distribution function is the measure, so to speak. Yes. So that's what I meant.
Okay.
So this is a formal thing if you want. So this one. So I have left that part as an exercise for checking directly. So you can make it a homework exercise, anybody who is crediting. Okay, so we get this. So the thing what remains is just to prove the claim. So if I have this function v, then I want to prove the sup norm of v is like this. Now we don't use anything about v actually, pretty much nothing. This is true for any v. We will do that. Okay. So any other questions? So now I start the proof of the claim. So v is a function from t to r, integrable. That's all I will need because it's true, it's integrable, right? F mu of t, these are all bounded functions. These are probability measures. They're bounded by 1. It's a integrable everything. And v hat of 0 is integral v, which is 0. 1 over 2 pi integral v over 0 to 2 pi, which is 0. Okay. So now we want to bound the sup norm of v. See, the idea is how can I bound? How can I get a bound like this in terms of the first few Fourier coefficients and the remaining? Okay. And the remaining is modulus of continuity. This side is modulus of continuity of V and the first few Fourier coefficients. How will I do that? The idea is we will convolve, okay, with the fair kernel. Sigma NV be equal to V star Kn. Kn is the fair kernel. I'll recall what it is, but you remember fair kernel is an approximate identity. It looks like this. This is how Kn looks. On here I have written it on minus pi to pi with 0. It is peaked at that point. So this is an approximate identity. So we have seen things like, so integral of Kn over T is 1 and Kn is always non-negative. So it's a probability density. So this is just I'm recapping what we know about fair kernel. The thing is it puts most of its mass inside. Okay, if I take the complement of a short interval, then what is the bound I have? Let me look up. Where was that? Fourier analysis on the circle. No. Right. Kn. Okay, very good. So on minus delta delta complement, the integral of Kn d theta over here I should have a 2 pi. That is, what is the bound I had? Yeah, where did I write a bound? It is this, right? No. Right. Okay. So it is basically this. Kn of theta, the formula is 1 over n plus 1 sine square this. So Kn can be bounded by so you can just bound the numerator sign by 1. Okay, so Kn formula is this. So let me just go and write here. So it is bounded by so remember that Kn of T is Kn of S is 1 over n plus 1 sine square of something by sine square S by 2, which is bounded by 1 over n plus 1 sine square S by 2. Now sin S is comparable to S, right? So if you remember, sine theta by theta is decreasing on 0 to pi by 2. So I want an upper bound. So I want a lower bound for sine theta. So sine theta by theta is greater than equal to sine pi by 2 by pi by 2, which means that sine theta is greater than equal by theta is greater than equal to 2 over pi. Okay. So we can write here, this is bounded by, let me just put an n here, and sine square will be bounded by S square by 4 into, so 2 theta by pi, right? 2 theta by pi, so 2s by, so that will give me s over pi. So what this gives me, if I put 2 theta over pi with theta equal to s by 2, that will give me s over pi. So I'll get something like pi square by s square. Pi square by n s square. N plus 1 n, who cares? Okay, so this is pi square by n square, which also, we don't care about all that pi and so on. So let's say it is bounded by 10 by n s square. So this Kn is bounded by 10 by n delta square. Because on the outside of, actually it is, outside of minus delta delta, it is bounded by that. Okay. This is true. This is bounded by, so this is what I can do. And the integral of du by 2 pi will be at most 1. So I have this type of bound, 10 by n delta square. This is the key point. I'm just recapping the fair kernel, which has these properties. So you may also remember that what this does is, actually, this is v hat of 0 plus j equals minus n plus 1 to n minus 1. 1 minus absolute value j over n or n plus 1 something. Okay, I don't care. Okay, there may be an n plus 1 problem, but times v hat of j times e to the I j. So sigma n v of t is actually e to the ijt. So this is how it looks. This also, you know, I mean, so this is how we had it. It's the average of the Fourier coefficients, right? So we had, yeah, where did we have? It's somewhere. Where is that? Okay, I forget. Where is it? Somewhere here. I mean, is that something everyone recalls that we had something like that? The sigma n will give me this. Okay, where is it? Okay, so I definitely did use it, but I now forget when I used it. Well, I did the fair kernel business, right? Okay, let's just take it. Okay, so this is something you have seen. I mean, so this is what you get because, yeah, okay. So this is what you get. Okay, so the point is what is the idea? So we want to bound the claim is sup norm of v. We have to bound using the Fourier coefficients of v hat and the modulus of continuity of v. So what we will do is that, so this is actually, so this is 0. The first one is 0. So what we get is that sigma nv sup norm. This is a pointwise thing. This is something I cannot do for the original v, which will have an infinite series. So this one, sigma n v of t, is something very simple. It's a trigonometric polynomial. It's a finite sum. Okay. So this is bounded by sum over j equals, let me write j equals 1 up to n minus 1, 2 times absolute v hat of j. Right? You agree? Because it is bounded by 1. Hat of minus j and v hat of they have the same absolute value. So if I put all the absolute values here, I get sigma nv sup norm is bounded by 2 times the sum of the Fourier coefficients. So I know that sigma nv sup norm is bounded by this, which I want. Okay, so let me make this k from 1. It is the same. Okay, so what I want to now show is that sigma nv sup norm and v sup norm differ by at most this much. That is because you are convolving by something which is approximate identity and it only changes it a little bit. That's the idea that we want to show. So now we want to show so what I want to say is that if this is large, sigma nv sup also will be large, but I have an upper bound for this. So that's what we want to do. So I want an upper bound for the sup norm of v in terms of this and some modulus of continuity business. Okay. So how can we do that? So, well, let's look at sigma nv of t. By definition, it is integral over the circle of v of t minus s kn of s ds over 2 pi. Okay, that's the convolution, right? That's the definition of this. So let's do this integration. Let's break it into minus delta delta, where I'm going to choose a delta, okay, plus the integral on minus delta delta complement of the whole same thing, v of t minus s kn of s ds over 2 pi. And here it is v of t minus s kn of s ds over 2 pi. Okay. So what I want to write is this is greater than equal to, first of all, this is negative sup norm. Let me make it as negative as possible. Even if I make it, if v is equal to its negative supremum on this entire interval, okay, on minus delta delta complement. even if it is as negative as it can be, the integral of Kn will only give me on this will only give me 10 over n delta square. So I get here into 10 over n delta square. And now here V is, how big is V? Okay, on this V is bigger than, I can say that V of t minus s. So you have this interval. Well, if I translate it, it is t plus the t minus s will lie in t plus delta to t minus delta, right? So this is where t minus s lies in this interval. So what I know is V of t minus s is greater than equal to V of t plus delta minus the one-sided modulus of continuity. So t plus delta is a point which is at most 2 delta from this point. Okay, and the one-sided modulus of continuity, which I defined, which says that it's the sup of Vt minus Vs. So if you see that at any point here, it is at least V of t plus delta minus omega V of 2 delta. So what I get that this is greater than equal to V of t plus delta minus omega V of 2 delta. That's how big V of t minus s is. But what is the integral of Kn on this interval? See, there's no absolute values I have to put. Kn is positive, okay? And there's no, what is the integral of Kn on this? Integral of Kn on the complement is at most this. Integral of Kn on the whole is 1. So this integral of Kn inside is at least 1 minus 10 over n delta square. So this is how we get a lower bound. So here it is close at least to V of t plus delta minus this. Okay. Any questions or anything here? So we are more or less done. So what you do is now you choose t such that, well, I can't say V of t plus delta equal to the supremum, but I can make it as close to supremum as I want, because supremum, I am not assuming V is continuous. So I don't say that V. Simplest would be to say you choose t plus delta so that this is the subnorm of V. Oh, okay. There are two issues. Let me make it so bigger than sup of V minus, let's say, omega V of 2 delta. I can make it as close to the supremum of V. Okay, I can make it as close to the supremum of V. So, and then, and delta equal to, okay, first I want to choose delta. Choose delta to be something like 10 over n. That's what I want to choose. And then you choose something like this. Okay, it doesn't matter. I mean, so don't worry what this subtraction is. I could subtract anything below supremum. Simplest is you assume V of t plus delta is supremum of V. Okay, so that is the same. But what you get is that sigma n V supremum is greater than equal to then subnorm of V minus 1 omega another. I just chose this so that I can just, I don't have new terms, but the same term, that's all. So I get 2 times omega V of 2 delta into 1 minus 10 over n delta squared minus norm V sup into 10 over n delta square. Okay, I didn't. So what happens when I put delta is 10 by n? So let's write this as norm V sup into 1 minus yeah, 1 minus this minus this, 1 minus 20, right? Minus 2 times omega V of 2 delta. This is what we get. Okay. So now I am picking delta to be 10 by n. So if you put delta to be 10 by n, so what is 1 minus 20 by n delta square? N into 100 by n squared, which is like, oh, something is fishy here. No, something is wrong. Is this n delta square? Yeah. So if I pick something is so if I pick delta to be that small, then this is no. I want something is slightly off here. Okay, so what is wrong? See, this is becoming negative, right? I want this to be like half or something like that. All I want this to be half or so. So, but I make a mistake somewhere here. I think 1 minus 10 over n delta square. Yeah, n delta square. So this is becoming 1 minus 20 by 100, but n is in the numerator. That is terrible. Okay, let me just quickly see what mistake I'm making. Yeah, what did I do? I mean, so something is like a
It's 1 o'clock.
So can someone see what is going on? I mean, so is it delta squared? It's delta squared, right? That is coming from the fair kernel. Sine square is there, so that will be delta squared. But something is, I mean, so here what I'm having to take is I will have to take delta to be 10 by root 10. I mean, see, all I want is that this is at least half. Okay, so what I want is
I think you can have a.
Go ahead.
Yes, so there was a integral there. So you bounded by something by delta square. Then there was an integral. So I thought you just took the delta square out, then some constant. But if you integrate that, that will become delta, right?
Oh, this one you are saying?
Yeah, where you approximated the Fedor kernel.
No. Oh, this integral. Okay, you are right.
There is an integral there.
Right. Very good. So this is right. So this is 10 over n delta. I mean, okay, 20. This is maybe 2 delta. So you get 20 over n delta, right? Thanks. So this is, so you saved the thing. So this is actually the error of the integral is over n delta. With the delta square, my error term would have been worse. So this is all n delta. Excellent. That is right. Okay, so then I have this same n delta here. Now I am good. Now it is you have picked the delta to be whatever. So what happens here? This becomes n by yeah. Okay, so this is actually so 1 minus 20 by n delta, but that is I am setting it to be 10 by n. 10 by n is not good. Let's make it 100 by n. Okay. Let's make it 100 by n. So that will make it 1 minus 20 by 100, which is 4 by 5, which is bigger than half. Okay. So let's say it's so this is bigger than half of the half of I made a small mistake here. This is sup of v. Not the sup norm. So what I get is that sup of sigma nv greater than equal to sup of v into maybe 1/2 minus 2 times omega v of something like 100 by n or 200 by n or something that I don't care too much for. So with this similarly we can do the other way. Similarly, sorry, I'm just going a little over time, but I wanted to finish this off. Similarly, you can do the same for the infimum. Infimum of this is the supremum of the negative. Half of sup of minus v minus 2 omega v of 200 by n. But with these two together, we get the sup norms. So we get thus the sigma n v sup norm is greater than equal to the sup norm of v by 2 minus 2 times omega v of 200 by n. Now you plug it back here. Now you are done actually. So we know that sigma n sup norm is bounded by this. So this is star. So from star we get everything we want. From star we get that the sup norm of v is less than equal to, now I get 2 times, okay, sigma n v sup norm plus 4 times omega v of 200 by n. But this is bounded by, we saw that it is bounded by v hat of k. K equals 1 up to n. So let me just put a constant plus omega v of 200 by n. Okay, so as stated, I mean, if I was careful, I would probably do get 10 by n, but yes, 1000 by n, something like that. So that is the end of the proof. Okay, I will stop here. Any questions or anything, I'm happy to take.